A key to the efficient generation of reproducible data products is to start planning and building the framework as soon as you start thinking about a new research effort. Then the continued creation and maintenance of data products should become a regular day-to-day practice throughout the research process. The challenge to starting early is that you are still trying to figure out the details of the direction of the research. You know you want to create data products along the way, but how do you decide when and where to do it with so many unknowns? One approach is to divide the flow of data through your workflow into modules, where modules are defined by the key decisions you make about how to process and analyze the data. This approach makes it possible to complete data products associated with the earlier steps in your workflow without having to resolve the unknowns about the steps later in your workflow. A good way to start is to think about generating well-organized data products as the input to your own analysis. If you start by doing yourself that favor, you will have the added benefit of having a product that is likely already pretty close to being reusable by your peers. The modules needed for any given environmental science research project are going to vary strongly with the nature of the research. But field-based studies do have a common feature that they generally involve collection of some sort of primary data based on instrument deployments or field campaigns. I use the term primary data to refer to the entry point of data into the scientific process. This definition distinguishes primary data from the derived data products we generate through the remainder of the scientific workflow. On the path to data analysis, we often need to pull data together from different primary sources to get it ready for perhaps some sort of statistical analysis or as driving data for process-based modeling efforts. The added value of the time spent aggregating and harmonizing data might represent another key decision point, because we might have to decide among several alternative analyses that could be applied to the same data aggregation. Even if we don't currently have more than one analytical approach in mind, we might discover a promising alternative approach over the course of the research. Trying this alternative approach will be easier if the data were already organized independently of the other analyses we've already completed. These data aggregations are then typically used to feed our analyses that seek to understand the causes of patterns in the data. Analyses represent another key decision point because we have to complete our analytical data products before we can decide how our interpretation of the results might fit into one or more scientific communication data products. Communication data products might include presentations at meetings, reports for stakeholders, or manuscripts submitted to journals. With this approach, we've basically mapped scientific workflow with a directed graph associated with data flow. The vertices or boxes of the graph represent the decision points where we want to generate data products as we work through the project. And the edges or arrows of the graph represent the flow of data driven by the data processing we need to generate each data product. The benefits of this modular workflow is that a given product at the initiation of the workflow is designed to be generically useful and not biased by any particular plans for later analysis. Therefore, you can get started on these data products at the initiation of workflow and complete them even before you make any final decisions about later analyses. Once we have identified when and where we want to create data products, we need a strategy for organizing the files associated with generating each product. The primary goal of that organization is to clearly distinguish the files representing the final product from those that provide the source data or those that define the protocol that generates the product. Also, we want to be sure that the data product is portable, so it is easy to share in a way that a peer could reproduce the workflow and verify they get the same results. One way to achieve this goal is to organize your files in what we call a pipeline folder structure. The idea of a pipeline is that each vertex representing a data product includes one or more edges that represent the data processing necessary to generate that product. If you're interested in organizing data to optimize reproducibility, a natural tendency is to want to keep each data product you generate together with the workflow that generates it. Therefore, we might think of each collection of edges leading to a given vertex as a pipeline for data flow through the project. If you visualize each of these collections as a pipeline, you can see how the entire workflow is covered by modular units. The products earlier in the workflow become the source data for generating products later in the workflow. Each of these pipelines might then be a folder in a file system where a collection of these folders represents the full workflow for a project. The next step is to think about how files are organized within each of these pipeline folders for a given module. While you can imagine a wide variety of folder structures that might be useful across differing domains, we suggest that a simple abstraction of 4 folders fits a wide range of scientific applications. This organization will avoid some of the worst sins in data management regarding the conflation of different stages and categories of data that should be kept distinct. The input folder contains unmodified copies of the source data that is used by the local workflow in creating the data product. This source data includes any metadata context from the data origin that needs to be propagated to the product. The input folder may be populated simply by manually copying files from their origin. However, a more robust practice may be to automate importation of files to make it easier to repeat the workflow if the origin of the source data changes. The input may either be a complete copy of the necessary source data, or it may be a reference to where the source data can be acquired if storage space is limited. With the exception of the automated import of the unmodified source data, data files that are created or modified in the process of generating the data product should not be stored in the input folder. The pipeline defines different folders specifically for these files to avoid conflating source data with derived data. The protocol folder contains any files that describe the local workflow for deriving the data product from the source data in the input folder. Note that we use a numerical prefix for each folder such that an alphabetical listing of the folders will be in a logical order for the workflow sequence. Files in the protocol folder may contain manually maintained narrative describing any manual steps or subjective decisions in the protocol. But for the sake of reproducibility, the most effective practice is to automate any parts of the workflow that can be automated. Therefore, the protocol folder should also contain any computer programs used to automate generation of the product, including the automated processing of the metadata. Practice of literate programming and the automation of both data and metadata processing is encouraged, where the automating code that minimizes potential for human error is embedded directly within a descriptive narrative that maximizes human understanding of the workflow. Using literate programming to automate the process of rendering a human-readable report aids in maintaining the integrity of the metadata describing the product. The product folder contains all the data and metadata files necessary to reuse the data set that is the final output of the protocol. The inclusion of thorough metadata in the product is critical to minimize the potential for the misuse or misinterpretation of the data in downstream analyses. Finally, the incremental folder contains any files that are created by the local workflow in the process of generating the data product, but are not considered necessary for reuse of the data. Files in this folder are thus considered incremental information defining the computational or analytical provenance for generating the product, but are otherwise not critical for use of the data in downstream analyses. Note that any reuse of the data product for downstream analyses should be possible strictly from the contents of the product folder. The contents of the input, protocol, and incremental folders of the pipeline should only be necessary for those who might want to reproduce the workflow that led to the contents of the product folder. Metadata describing a workflow has a tendency to become stale if the maintenance of that metadata is too far separated from the maintenance of the data files that are the target of the workflow. Therefore, the final key practice for the day-to-day generation of reproducible data products is to tightly couple the maintenance of metadata with the maintenance of the data analysis and process. With the goal to automate everything that can be automated, let's review an example that involves using the tools of literate programming. Specifically, let's talk about how tools like R Markdown can integrate the generation of a report describing a data product directly with the R code that generates the data product. First, we have some sort of raw data file that describes the source data needed to generate the data product. Perhaps in this case, that is some sort of tabular data in a comma-delimited text file. We might also have a file with any transferred metadata describing the source data, which allows us to propagate that metadata to the data product. These files may be in many different forms, but let's just say for this generic example, it's some sort of text file. R Markdown lets us define a single source code file in the protocol folder that contains both narrative metadata and code. Markdown is a text formatting language that defines the formatting for any narrative content in the R Markdown file. The R code is then embedded in the Markdown code. R Markdown uses a tool called knitr to find and run all the embedded R code it can find in the file. knitr can then be configured to take whatever text is generated by the embedded R code and put it back into the Markdown text at the location of code that generated it. Then the remaining text file is only Markdown code that can be turned into other types of documentation files to produce a human-readable report. The resulting Markdown is thus a mixture of narrative content maintained in the original R Markdown file and automated content generated by the embedded R, giving the author flexibility in automating as much or as little of the content of the generated report as desired. Therefore, the code embedded in R can do the job of generating the data file for the final data product. And in the process of R Markdown running that code, a document describing how the data product was created is automatically generated and stored alongside that data product. In this case, the resulting Markdown is translated into an encapsulated HTML file that can be opened in human-readable form in any web browser. A common name used for this type of metadata file is a strong hint to the user that they should perhaps read the content of the file before using the data. The metadata might also be handled by the embedded R code in a more structured fashion, allowing the automated generation of structured metadata files that are sometimes required by data repositories. In this case, we might want to submit to a Data 1 repository that requires an ecological metadata language, or EML file, that is formatted in an extensible markup language, or XML text file. The generation of reproducible data products requires development of a wide range of skills and practices. However, starting with just these 3 key practices will get you pretty far down the road of generating data products with the basic traits that make them truly reproducible. And perhaps just as importantly, this approach to these fundamentals gives guidance that promotes immediate implementation at the initiation of data collection planning. Day-to-day practices that naturally and efficiently generate reproducible data products throughout a project require strategies that allow you to start early and work on it in shorter increments. This approach will keep the work of data curation from exploding into an onerous death march at the end of the scientific workflow.